on how you can understand and implement tf-idf in code. So we are going to look at two different approaches. Number one is going to be coding it straight up from the mathematics, the formulas. And number two is going to be looking at it from the production point of view, where things are mostly done with the scikit-learn library. I mean, there are more ways to do it, but turns out scikit-learn is very industry standard, and that is what we're going to look at today. So I have pulled up a notebook over here. I've already put in all of the required mathematics over here. I will not go into the details of how exactly the formulas are calculated. They're pretty easy and understandable and approachable. But still, let's go through the process once. So to calculate tf-idf, you generally need 3 steps. Step number 1 is that you calculate the term frequencies, and that is determined by this formula over here. So the term frequency is the number of times that the term t appears in a document, and we normalize it by the number of terms in the document t. So like if you have a term that appears 5 times in a document and your document has 10 terms, then tf is going to be 5 divided by 10. It's that easy. The second formula is the inverse document frequency. That's the IDF part of tf-idf, and it is determined by this formula over here. This is the crux of it. We are going to arrive to this formula later. So it's very easy. So let's say you have the total number of documents, and then you divide it by 1 plus the number of documents that contain the word t. So let's say you have 5 documents, and the word t is contained in 2 documents. So this is going to be log of 5 divided by 1 plus 2, which is log of 5 by 3. And that can be calculated. Now, why we're doing a 1 plus over here is that we don't want to divide anything by 0. Let's say the term t that you're searching for is not available anywhere. In that case, it will be n by 0, which can be catastrophic. That is why we do a 1 plus. This is called a Laplace smoothing, and we can apply this even further. So we can actually go log of this plus 1, so that we don't have a term that's actually 0. Because if we get an IDF of 0, which I'll come to later, the tf-idf is actually calculated as tf times idf. If idf is 0, tf-idf becomes 0. So that's bad. So we don't want that. We just want everything to be 1 and maybe greater than 1. So that is why we are doing a 1 plus. And we can also do the same thing for n plus 1 over here. Now, this is done in Laplace smoothing. Why I want you to look at this formula is because this is what is implemented inside of scikit-learn. And if you're calculating it manually and you're doing it with scikit-learn's API, then sometimes the results can differ and you might be confused. So that is why I wanted you to look at the formula that is implemented inside of the library. So with that out of the way, we can now go ahead and start writing our code. So like always, we'll start with a few standard imports. So I'm just going to import NumPy first. Import NumPy as NP. I'm going to import the standard math library next. And since we're going to calculate stuff, count stuff over here, like we have to count n, we have to count how many times t appears. That can be easily and neatly done in Python with the counter library. Okay, actually, collections is not a library in itself, so we have to import it from collections. So it will be from collections import count. Let's go ahead and run this. And everything is installed. If you don't have NumPy on your system, you'll have to install it first. So make sure that is done. So once we have done that, we can go ahead and declare our sample corpus. I'm going to keep it very simple. Let's just make it a list. So this is going to be our document 1, sample document here. So what we're going to do is this, the first line is our document 1. I'm going to shift that up. Okay. So now let's define a few more documents. This up here. And let's define 2 more documents like this. Like this is a sample document. Now you'll see that over here I have repeated sample document twice. This is done intentionally. You'll come to know it later. So this is document 2 for us, and maybe another line, something along the lines of samples are maybe not samples. A sample is a good way to check the vibe. This is just a random line. I just wrote it up. Don't take the meanings of this seriously. But whatever I'm doing over here is intentional. The presence of the is intentional. Presence of a is intentional, and you'll come to know about it later. So this is our corpus. We have 3 documents, and each of these 3 documents has have these lines inside of them. So we are going to do tf-idf calculation on top of this corpus. So when I say document D, it means an entry in corpus. when I say term T, that means a word inside one of these documents. So let's go ahead and yeah, so that's done. So now we can go ahead and start calculating TF. Before we do that, very important step in any NLP task is to do tokenization. Now, I am not going to do any fancy tokenization with an NLTK or something like that. I'm just going to do is what I'm going to do. This is a very simple way of looking at tokenization is that if we have a sentence, I'm just going to write it down. So let's say we have the sentence sample document here. Okay. So if we are going to do a very bare bones tokenization, what we want is an output like this. Output after tokenization should look something like this. So we need to have a list. Sample should be an entry. Document should be an entry. And here should be another entry. So this is the very basic form of doing tokenization. And at least we want this. I mean, there are much more fancier ways of doing tokenization. This is not the state of the art, but this is a bare minimum that we need to do. So let's do this. This can be done very simply. So let's say for Word, for a document in corpus. So this is going to give us each of the individual entries. So if I go in and print the document, you'll see that we are getting the sentences. So what we need to do on top of this is that we need to convert them to lists and print it in this manner. So what we can do is we can use an inbuilt split function for this. So if I go ahead and split them up, so now you can see that each one of them have become lists. And this can be considered a tokenized corpus. But we just need to do it in a fancier way, put it into a way in which we can do further processing. So for that, we'll rely on a bit of Python magic. So what we can do is instead of relying on a very legacy form of code, we will use a little bit of Python magic over here. So we want this to, first of all, we want it to be stored in a variable. So let me go ahead and define that. And after that, what we can do is for Word, let's say for document in corpus, we want the split. We don't want to split them up. So document.split. And this is going to do the same thing what we did over there. So, but instead of printing, we're going to use the built-in the way that's the Jupyter notebooks, and it's the same thing right now, but it's stored inside of a variable, and we have also made this into a list so that we can iterate it. So now we have the tokenization done. Now we can go ahead and do the first step, which is calculate the term frequencies. Now, calculate the term frequencies is very straightforward. So we have the very simple formula here, number of terms, a number of times the term T appears in document D, divided by the number of terms in document D. So first off, we need to calculate the number of terms in document D, and that can be done in a very simple way. So we can just go for word in tokenized corpus. Let's just look at what exactly this word thing is. Turns out it's not a word, it's printing all of the documents over here. So what we can do is the number of terms in the document D can actually be our, I think I should rename this to document just so that it becomes more clear as to what we're trying to do. And then if we are doing length of document and we want to print that out, so that will give me the number of words in each and every document. So the first document, we have 3 words, so we got 3. Second has 5 words, so we got 5. The fifth has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so we got 10. So this is fine, this is working. We have the denominator figured out. So now what we can do is instead of printing them out, we can just go ahead and define like a list word doc length. Let me just define that to be empty list. And then what we can do is instead of printing them, we can do doc lengths dot append, and then we can append the length of the document. Now, if you print this doc lengths, so that gives us a list of the numbers. So now we can iterate on top of this doc lengths and calculate the TF, which is going to be pretty easy. So we just need each of these words, and for each of these words, we are going to calculate this. So first we have to go inside of the document, get the word, and then calculate the list. Okay, so now while this is a very valid way of approaching the problem, it's also not the very the best way to do it. We want these numbers as well, but if we don't have a count of what exactly they stand for, it's kind of irrelevant. Now this is where the counter library comes in, which we imported over here. Now what the counter library does is, for a given length of string, it will just, for a given string, it will just count how many times each and every word is present in it. So we can just go ahead and do a little test run with it. So if we go ahead and do counter of tokenized corpus of 2. So tokenized corpus of 2 is this sentence over here. So if we do a counter, and it's going to give us an output like this. What it means is that A appeared twice and everything else appeared once. So A appeared twice over here and over here. And that means that for each and every word, we also have the frequency of how many times they appeared within a sentence. Now, why this is useful is that when we are calculating it with counter, first off, the code becomes clean. We don't have to write 2 lines and a for loop inside of it. So that makes it cleaner. And number 2, we also have more information and we'll be using the words that the counter library returns. Okay, so what we can do is while we're iterating over our corpus, we can just go ahead and store these inside a variable called term counts. And then inside term counts, how we're going to define it is that we'll just put the documents through counter. So now if we go ahead and print the term counts, we can get the exact frequency distribution that we were getting over here. It's just going to be a much simpler way to do it. And also it gives us much more information rather than our hard-coded implementation, which should have just taken up more space. So once we have that, we can go ahead and get the sum of each one of these counter variables. And that is going to give us a number of terms. And we also have to calculate the number of terms times term t appears in one document. And since we are iterating over each one of these documents, if we just do a very simple length of term counts, and then if we go ahead and print that out, it's going to give us the length of each one of the sentences. And one good thing that we got over the last implementation is that now we are only taking unique words. This is a very neat thing, which is why I try to use counter instead of going the traditional hard-coded way, is that if we have a single word that's appearing more than twice, we don't want to calculate the tf value for them twice. We just want to do it once. And that is very neatly implemented with counter. So now we have 3, 5, and 9 instead of 3, 5, and 10. It's because one of the A is repeated in the last sentence, and now that's gone. So once we have the term length of the term counts, we can just, instead of printing that out, we can just store that in a variable. So let's just name that length of terms and keep it over there. So now we have everything that we want to calculate our tf values. Inside of counter, we have each one of the words, and inside of length of terms, we already have calculated the denominator. So we just have to do the division and return that. So what we can do is I'm just going to print this out for the beginning. So we want to do is for term in term counts. Just for a test run, I'm going to show you how exactly this will work. So for term in term count, if I go ahead and print out the term that we are getting, so this just gives us the words. That's exactly what we need. So this just gives us, let's remove this. Yeah, so A appears twice, sample appears once. It's a very neat way to do it. So we want to do a similar thing over here for term comma count in term counts dot items. So now we have the term and we have the count. We just have to do the calculation. So let's say if we have the count for each of the words, that becomes our numerator. So it becomes count divided by, and we have the denominator already calculated and stored in length of terms. We can just go ahead and print that. So what this will do is it will give us the TF scores for each of the words. And if we just go ahead and run this, you can see we are getting objects printed out. So instead of printing them out like this, what we'll have to do is we'll have to put them inside this. And that gives us the TF values. Now, if you look at it, it just gives us one of the values. It's because there are more than one that's calculated, but it's getting truncated. So there's a neat way to combat this. So since this is a dictionary, that is the problem. And if we just put that inside, like this is a key and this is a value part of the dictionary, and that gives us the TF values for the entire corpus that we have. So instead of printing them, I'm just going to store it inside variable. So tf values equals to that. And then if we use Jupyter's advanced ready printing thing, it's going to be much cleaner. Yeah. So this gives us 9 different values, I guess. 3, 4, 5, 6, 7, 8, 9. That's because there are 9 unique words in our corpus. Rest of them are repeated words, so that is automatically truncated because we use counter over there. It's a very neat way to do it. And we also don't need this variable anymore, so I'm just going to delete that. And now we'll have to think a little bit about reproducibility of the code and reduce redundancy. So instead of making a for loop run like this, we can clean it up. Let us define a function that will do the computation of the TF for us. And to this function, we're just going to give one document at a time. So this becomes a little utility function. On itself, it's not going to give us anything. I forgot that the function has to return something. So you can do it like this, or if you are chasing the maximum efficiency and reducing number of lines of code, you can do that. So it's a neat way to do it. We just have 3 lines, calculates a compute, or the calculates a TF value. So now what we can do is we can define TF values again, but we can now use list comprehension to neatly do it. So I'm just going to put it. So let's compute TF for the document, and let's get each document out of our tokenized corpus. So, and now if we go ahead and print that out, hopefully we will get the same thing, which we did. But this time, instead of getting a compressed list with just the unique words that were in the entire corpus, since we have done a little for loop and then we have run it separately for each of the times, giving the function only one document to look at a time, it didn't get to compress the entire corpus. So we have, for each of the words in all of the documents, we are calculating the TF values and printing them out like this. So this is the first part. We have our TF values now. Next, we can go ahead and start computing the IDF. So we'll do that next. So IDF is also, we're going to take a similar approach to calculating IDF. First, we will find out how to calculate the numerator, then we'll find out how to calculate the denominator, and then the log is just a math.log. So we have already imported math over here. We're going to use that. Okay, so let's go ahead and start doing this. First, I will do this formula, then adding the smoothing is just tweaking that same line of code. So there's a very neat way to do this. Now, if you remember, we had tokenized our corpus and put it into this format. I told you there was a reason why we did that. It's because for each of the documents, we have a 2D list, and each one of them contains all the words inside of them. So now, for the outer array, when you're looking at it from the outer array, there are 3 different items inside of the list. While all of them themselves are lists, each one of these lists shows you how many documents there are. So if we just calculate the length of the tokenized corpus, we are going to get the length of the corpus, number of documents in the corpus. So we can just do that. So if we do length of tokenized corpus, they're going to give us 3. And because we have 3 documents in our corpus, if I go ahead and add another into this, like sample document will calculate. This is our 4th document. So now if we go ahead and run this, length of tokenized corpus is going to give us, okay, we need to tokenize it again. Okay. So now we have 4 different entries in our corpus, and I think I should go ahead and run these ones as well. So you can see it automatically updated, just because of all the thinking that we had done beforehand to make the code reproducible and not as redundant. And the length of tokenized corpus is also 4, so that works, we know. So we have calculated the numerator. Now we need to figure out how to do the denominator. Let's look at it this way. So 1 plus something. 1 plus is simple. It can be done. We need to think of how to do the something part of it. So the something is the number of documents in your corpus that contains the term that you are looking for. So step 1, I'm going to think about it this way. Step 1, find out how many unique terms you have in your corpus. Remember that while calculating the TF, we had accidentally stumbled upon that part, which gave us a unique list of all of the letters in our corpus. That's exactly what we're going to use over here. So we have to find out the unique terms in the corpus, and then for each one of those terms, we'll have to find out in how many documents they appear. So find out how many documents contains each one of the unique terms. So two twos over here. I'm just going to write. Right, so let's get started. What we want to do is very simple. We have the tokenized corpus. We print that out. This gives us all of the terms in the corpus. So let's just iterate over. For doc in tokenized corpus, this is a little thing that we have to do right now because we have done the document segmentation thing. We didn't go for the other option. We don't have another way to do it. So I'm just going to print one of the docs. So now we have 1D lists. And for what we can do is for word in each one of these docs, let's print them out. We'll get all of the words that they're in. So now we just need to eliminate the words that are appearing more than twice. So what we can do is, it's a very simple way to do it, and that is by using the set function in Python. So what set does is it takes a list, and then if there are any item that's repeated more than once, it'll get rid of it. So I'm just going to define a list, unique words. Okay, pretty quickly, unique words. Okay. And then instead of printing the words, let us go ahead and append list. So now we have this list of all the words that are in our corpus. So if we just go ahead and do set of this thing, it'll get rid of all of the duplicates. So let's do that. There we go. So these are the only unique words in our corpus. And we need exactly this. So instead of writing so many lines of code and acting like this is C and not Java and not Python, I'm sorry, let's use some Python magic. So we want to calculate the set, that much is confirmed, but we want to do them for each word in a document, for each document in tokenized corpus. It's a very easy way to do it. So we can just use nested list comprehension quickly. So if I go ahead and comment this, that out, same thing. But instead, this time, we are just using one line. Okay, so this is going to be all of the unique words that are in our corpus. So let's just save that inside this. And that's it. We have compressed it successfully to one line of code. Just fantastic. So now we have the unique words. We just need to go from term to term in our corpus and check how many times they appear in each dictionary. In each document. So let's just quickly get started with do that. So for word in unique words, words is not the best term for this. Actually, I would prefer this to be terms, because it could be a word, it could be something else. So let's go ahead and term in terms. So once we are inside of this, we can just go ahead and print them. So we are just doing a very simple thing. We are just taking out all of the term inside our corpus. So once we have that, we can just go ahead and calculate the IDF for each one of them. So we have our n over here. So I'm just going to define that. Just use that. And so it's going to be, it's very simple. So what we want to do is math.log of n divided by 1 plus. Now is the tricky part. How do we calculate df of d? So we just want to know if for every term in that set of our unique terms, if that is present in how many documents. So it could be present in one document, it could be present in more than one document. We don't know. We'll have to calculate that. I'm just going to comment this line out over here. For every word, let's go document to document, which is and let's find out if the term is in the document. Then let's keep a counter. Let's like count equals to 0. And if it is a document, we just set that to 1. Let me just add that, increment that by 1. So once this has finished processing, we have the count. We'll just go ahead and print the count and check out what we exactly calculated. So this gives us, this is not really interpretable now, is it? So let's do term and count. This is going to give us a more idea of what we're looking at. So, sorry. There we go. So the term is vibe is present once. The term is present in one document. Term u is present in one document. Way again, but you see A is present in 2 documents. Sample is present in 4 documents. Let's just quickly go ahead and verify exactly what we are looking at. So if we print out tokenized corpus, you'll see that A is present in this document and this document, so it's fine. Sample is present here, 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 and here. 4 documents, so that is fine too. And similarly, document is also present. Document. There's no document here, but document comes back, so it's 3 times, 3 documents. So this is fine. We have this counted out. Now we just have to, once we have the count, we can just go ahead and calculate this formula over here that I was trying to write. So what we can do is, so term count, it's going to add IDF value. Let's put that in math.log 1 plus. It is the count, and that's going to be our formula. And then let's find out what we just calculated. So these are the IDF values. So as you can see, there is a negative value over here. There is a 0.0 over here, which is going to be catastrophic when we multiply it with the TF values to get the tf-idf, because the value of 0 won't really tell us much. So we have to do some fixes to this formula. That is what is done with Laplace smoothing. So you can read the theory over here. You can also read it up in detail online. What it does is it modifies the formula in such a way that we don't get negatives or zeros because of how log works. Because if you are trying to calculate the log of a value less than 1, obviously it's going to give you a negative number. So let's go ahead and fix that. So first stop, the fix that we are going to do is look at 1. That already fixes a lot of the issues. The negative value is gone. There are no more negative values. But if we are still looking at some zeros, there's 1 0 over here. If it's a bigger corpus, the problem could be bad. So we are not going to do much. So let me just put this entire thing within a bracket. What we are going to do is a very clever thing. We're just going to add 1. And that we will bring everything up to 1. So 1 is going to be the least value that a IDF value can have. That makes sense because we're going to multiply it. We're going to multiply it with the term frequencies to get the tf-idf. So there we go. The least value is 1, and it can go high as depends on your corpus. But over here, we are getting something like 1.916 to be the highest. Now, if you know how IDF works, if you have read up on the theory, you will know that a high IDF means that your term is rare, like it doesn't really appear in many documents. And a low IDF means that your term is not rare, it appears in all of the documents, like articles A, and D. These are not rare words, everyone will use them in a collection of documents. So they have a low IDF, and that is done with a 1.0 over here. Now, if you look at this corpus exactly, you will not get the very clear idea of how this is going to work, because we have just written some random sentences for our corpus. Document will not exactly look like this, but once you do it in document scale, these numbers are going to make more sense in the way that I'm saying. Okay, so once that is done, we can now go ahead and instead of printing them out, we can just IDF values. Let me do the same thing that I did for TF, because we want to have all the numbers in a list. So instead of doing that, we can just go ahead and append that to a list. Then return the list, we'll put it inside a function, and that is going to make things clean. Do we have missing words? Okay, so this is going to do the work for us, but this part of the code again isn't looking that good. So what we can do is we can use Python magic again. So both of these can be in the same line. There we go. And let's just say if we find it, then we are going to set it to 1, and then we are going to sum them up. So what it does is exactly it's going to do the same iterations, and for each of the iterations, if you find it, we are going to return 1, and then we can just put this inside a variable. Put this inside. So now we can do this in just a single line, which is neat, and it's going to return the same values. Mute the printing to bring it back. Okay, and this gives back the values that we calculated. Really. So we can look at it. It does the same thing, but now it's just 2 lines instead of so many lines. But we really want it to be more interpretable, like we had done for tf values. We had a nice dictionary going, so we want that dictionary thing again. So this is just a list, and it's not the best way to do it. So let's convert this to a dictionary so that we have maybe not as robust as this, but something that's iteratable, something that can be iterated, and easily we can make sense of it. So what we can do is term inside like that, and we have to set this as a dictionary entry, and that's going to make it a lot better. So it's the same thing, but instead of this, let's go ahead and print out the dictionary that we just filled, and this is a much nicer way of doing it. So once we have all of this figured out, we can just put the entire thing inside of a function like we did last time, and that's going to make it. So let's just go ahead and define the name of the function. We're going to call it a compute IDF, and since the token IDF calculation works on the entire tokenized corpus, we're passing the entire tokenized corpus. Got Python syntax. Okay, so once we have done that, we can just use a single line. I think I should move this part of the code inside this way, and we can go ahead and delete that. The to-dos are both taken care of, so we can remove that as well. So now this is our utility function that will, given a tokenized corpus, is going to calculate the IDF, and it's going to return that in a nice dictionary. So let's just put this into action. So IDF values equals, and then we can just pass the tokenized corpus to it. There we go. Let's just look at it, see if everything is fine. Now there's a little problem, and that's this is a list, and the list has individual dictionaries inside of them, and that is because I've done a bad mistake over here that I should have been more careful. So instead of appending, which makes it a list, we cannot use appending, and we definitely cannot do it this way. So what I'm going to do is let's just say IDF value equals to that. So this will give us our IDF value, and then what we can do is IDF values is the list that we have defined over here. So IDF values of term, that will equal our IDF value. So this is going to make sure that this follows Python dictionary syntax, and we are not making a mistake like this. So let's just go ahead and return little errors here. We try to make a dictionary out of this, and that works. Now we don't have a list that contains dictionaries inside of them. We have an actual dictionary, and now we have calculated both our TF values over here, and we also have our IDF values over here. Now we just have to multiply them, and that will give us our tf-idf. So let's do that. Now, if you look at the tf values closely, it is a list that contains dictionaries inside of them. So let's just try to find out what exactly going on inside the tf value. If we print the tf, then what exactly does it look like? So each one of them, each one of the tf is like is a document with all of the terms inside the document, and we want to calculate the tf-idf for all the terms inside a document. So this is particularly helpful. All right. So what we want to do is we want to go through each one of the terms, each one of the documents, and then calculate tf-idf values for them. So we can just iterate that and print out what exactly we are working with. And this gives us all of the terms. document-wise organized. So we can just use these terms and calculate the tf-idf values for each one of these terms. So let's do that next. So once we have the term, and since both our IDF is organized according to the terms and our TF also contains the terms, we can just simply do TF of term, and that's going to give us the TF values for each one of the terms. And then if we go ahead and multiply that, the same logic, IDF of term, so that's going to give us the tf-idf values. That's it. It's that simple. Next up, we just want to clean the code up, put it into a dictionary, because that's really helpful when you're trying to iterate the corpus and the tf-idf values for all of them. So we also want to do a little bit of Python magic. So I'm just going to put that in here. So instead of printing, let me define a dictionary again, like last time, tf-idf values, and for the dictionary, and then, or if you want it to be like a list, which I believe will be better in this case. So what we exactly want to do is we want to make this list in such a way that it has all of the lists, and then each one of them has the term, and it also has a tf-idf value that we have calculated. And what we can do to do that is that we'll do a pen, but this will just make it a run-of-the-mill list. If we do that, you can just see spreading out objects, not really that helpful. So let's convert this into a dictionary instead. And so this is going to be a key, this is going to be a value, and then if we print that up, this is much more helpful. Because now we have the key, which is the word, and the calculated tf-idf value for that. So let's go ahead and fix the printing. Okay, so once we have done that, if you print that out, we get the same thing that we got last time. So you'll see that just like the TF values that we had calculated, we get a dictionary, and each one of those dictionaries contains 3 entries for the first one, which is exactly the sample length of the first document that we had. So sample document here, each one of them has the dictionary values. Why I put this into such a manner is that if we go ahead and start printing them out, so we also have a sense of which document we are looking at. So if we do a little printing, so we can just do for I, doc in, let's enumerate the dictionary, which is that one. So we go ahead and print it out. So we could directly access the document we are looking at, which is pretty important when you're doing tf-idf. So we have the document number printed out, and we also have, and inside of each one of the documents, we will also have the tf-idf values, which is pretty neat. So let's just go ahead and put that. So it's going to return this part of the document. And there we go. We have a very nice way of putting it all together. So document 1, tf-idf values at that. Document 2, the tf-idf values at that. And each one of these docs that we're printing out is a dictionary, so you can further iterate it and use it as per your project. So that's building the entire thing up from the mathematics. Now let us look at how to do it this thing using the scikit-learn library. Now this is going to be a little bit abstract in a way that scikit-learn does a lot of stuff behind the scenes for you. So this is a code that you need to import the vectorizer. Don't ask me why, don't ask me how. Scikit-learn. So scikit-learn has feature extraction text, and inside of it they have tf-idf vectorizer. So we have to, this is an object class, this is a class, we need to instantiate it and make an object out of it. So if we just call it tf-idf vectorizer, so this is going to give us the object. Let's store it inside a variable so that we can use it. Now if you print out the variable, it's going to give you the object. We need a sample corpus again. I'm going to define a new one. This is that we have a count of what we are looking at. This is a very simple one. Not the lines of the corpus that we work with, but just one. Now we're going to work with NumPy arrays, and we're going to make everything into a matrix and then use that matrix like we always do with while working with vectorizers. It's because this makes it very easy when you're working with large documents, and it's very important to make your code in such a way that it works with large documents, because you'll not be working with corpus like this at all. if you print that out, you're going to get random numbers like this. Don't worry if this doesn't make a lot of sense to you. It will make some sense very quickly. So now we can go ahead and so first off, before we want to work with is that we want to calculate the unique set of all of the terms in our corpus that we did over here. But instead of relying on hard code that we did over here, we are going to use the function that is built into sklearn for this. So that's called get feature names out, and this is going to give you an array. So let's print this quickly. Right. So you see, this just gives us a very simple list. And this list contains all of the unique words, but there are some differences. Now, for you to understand exactly what sort of differences we're looking at, let's check this again. So before you go ahead and do that, this was our tokenized corpus when we did it by hand. And then we calculated the unique terms. Just quickly print them out. Let's go to what exactly we're working with. So instead of that, let's go ahead and the unique term. I don't know what the idea of that is. Okay. All right. Yeah. So the unique terms were this, and this is what we were working with. And our tokenized corpus was this. But now when we do vectorizer.getter get feature names out, it's going to look a bit different. Need to fit it again. Look a bit different. What's going to look different? So let me quickly pull this up. Like I say, you see when we had tokenized it, and then we calculated the unique terms, things are looking much different. Yeah. So you see A is present here once, and so is the present here. But if you look at it, A is absent. Now, if you are looking at it like why did this exactly happen, the logic is the same. It's because what calling this function does is that it also does an automatic stop word removal for you. And stop words in English are these trivial words like A and stuff, for which we were getting very bad tf-idf values as well, because they are kind of present in all of the documents that you're looking at, almost all of them. So it doesn't really make much sense to calculate the tf-idf value of a number that's going to appear everywhere. That's just stupid. Why would we do that? So instead of wasting compute on trying to calculate tf-idf for these stop words, what sklearn has done is that they have completely removed it so that you don't have to worry about it at all. Because when you're doing a tf-idf calculation, you're not worrying about stop words. These are like the words that will appear in every paragraph, every document that you write. So once we have the feature names out, we can store them. Variable very quick, and that out, it's going to do the exact same thing. Now this matrix has to be converted into an array, so let's do that. Matrix to array. This does it gives us a sparse matrix representation. It's very important to go into these so that you can utilize parallelization, GPU architectures for the speed of tf-idf calculation. Otherwise, if you're just going to work with like Python integers, it's going to be very slow when you're working with very large documents and a large number of documents. So it's going to store this inside matrix. Store it in the array. We have the array. And it is going to do the same thing for us. And what it does is it just goes through each one of these. So we have done it in the same way. There are lists for all of the documents, and then you can just directly print them out using this. So just print them. I'm going to give you all of the tf-idf scores. Now you can see that still there are zeros in this one, because sklearn's implementation is not doing the final Laplace smoothing that we did over here. So if we want to get reproducible numbers, we'll have to cut that out and run this again. Let's calculate tf-idfs, and now the numbers are going to look similar. Now they're not going to exactly match because this one is using NumPy, which is higher precision, but we did using Python integers, and that there is some loss in precision in that. So it's going to look a little bit different, but it's the same thing. So that's about it for tf-idf calculation. What I find is that when I'm reading research papers and trying to understand, it's very important to have this in-depth intuition of how exactly it works so that you get a better idea, especially in NLP. So I hope this video helped you with that. If you want to run the code, I'll have it posted up. I'll clean it up, of course. I'll post it on Google Colab. You'll find a link to that in the description of this video. You can go ahead and run it and check it for yourself. And that's it. I will see you in another video discussing more about statistics, NLP research, stuff like that, whenever I'm interested.